Good morning, everyone. I don't think anyone in this room is unfamiliar with the existence of subject knowledge analysis, but we'll try to situate it and talk about how we do it a little bit. So subject knowledge analysis is a component of the Aries runtime, and it is specifically the most necessary component for the goal of not go fast. Right? This is something I've been talking about and promising for quite a while, and it's not obvious looking at Nock from the outside that this is actually possible. So rather than dive right in and say how it is actually possible and what the challenges are and everything else, I'm actually going to let Joe go ahead and talk about how he spun up on it and what it can do right now.
So I've been a big booster of this effort since Edward started it. And we have routinely talked, roughly weekly, about the details of the approaches that he's taking, progress that he's making, the obstacles that he's run into, and so on. But I really haven't worked on it until the last month, roughly around the Lambda Conf, maybe a little after.
The handoff happened right after.
And so part of the challenge for me has been because I've sort of been too close, but not close enough to really have all the details paged in, that I have, completely lost track along the way of the cut points between the various approaches here. So about a month ago, I dove in real hard, fully, with the goal of getting the analysis to complete for the Hoon compiler. So at this point, through many revisions, many different approaches, subject knowledge analysis is completely implemented. The linearizer, the SSA form, IR, code generation from the output of the subject knowledge analysis is totally working. And to give you an idea of precisely what it was capable of at that point, the entire Azimuth L2 code stack, something called libtiny, something called libnaive on top of that. Libtiny is a tiny subset of the standard library, only what's needed for the L2 transaction engine, but it's still, over 1,000 lines of Hoon, all the basic atom operations, some collection stuff. And then libnaive is the L2 transaction engine. It's a non-trivial state machine. It has a full Ethereum block parser and serializer. It has all of the Azimuth logic because L2 is a superset of L1. Non-trivial functionality. The point Edward handed this off to me, the analysis and code gen on that ran in a second and a half. So this is totally practical, totally real. When I tried to run it on Hoon.Hoon, I gave up after a couple of days. So what was clear immediately was we're redoing work. We're redoing work over and over again, but how and what? So the first thing that I did was I wrote a parser and serialization formats for the spot hints that encode file path, line and column ranges, wrap them around expressions, and started running that on Hoon.Hoon. And that gives you an exact trace of the abstract interpretation that subject knowledge analysis performs. So let me back up now and talk not about the details of the approach, which Edward will explain, but just what we're looking at and some rough conceptual models here. So the leftmost column is a status indicator, right? It's sort of saying what operation we're performing or what conclusion the analysis drew. The next column over is a call site identifier. This is simply a sequence number. Every new subject and formula pair that we analyze That's a new call site, it gets a new call site number. And then, depending on the conclusion that we drew, we may have just line and column range, or we may have line and column range pointing to a prior call site. We detected recursion. We may be memoizing analysis that we previously saw, and so we'll see the whole range of outcomes. But this first step was completely necessary just to even understand what we were looking at all. So now I'll say what the categories, what can happen when you show up to analyze a formula.
Do you want to tap over to that comment? Be helpful.
Yeah.
Oh, wow. It's
That
was the
is the analysis of whom.whom. And it takes about an extra 30 seconds because of all the debug output and all the processing that's involved in extracting all the debug output. And I did this without any special optimization of what Edward wrote. I didn't find some new representation for the tree types that he's going to talk about. I didn't find some, horribly buggy, asymptotically poor, iteration that he had written or anything like that. The only question was, how can we reuse the work that we have done that is not totally finished and timeless? So let me try to show you what I mean exactly by that. Holy crap.
That's good.
In the analysis, you are given a subject and a formula. The analysis is abstract interpretation. It looks exactly like a knock interpreter. The challenge and key of the analysis is it must discover the structure of the computation represented by this subject and formula in such a way that the structure of the computation, the parts of the subject that are used as code, are separated from the parts that are used as data, and you can generate code that will be applicable to many subsequent runs of the same code without over-specializing to the data that was involved. But it starts out, depending on your perspective, with nowhere near enough knowledge or way too much knowledge, because all it has is the actual subject that was given as a noun. The possible outcomes here are this analysis is memoized. We have already seen this exact formula and a compatible subject. We have fully analyzed it. We have finalized that analysis. We know it fully, permanently, totally. We know exactly what this is. Sort of the equivalent of matching a jet. It's complete, it's total, it's never going to change. We know everything about it. We'll just reuse what we've already done. We're going to skip the second one because that's where the magic happens. The third category here is pseudo-recursion. Now, because this is abstract interpretation, you have to do something about.
I think you should define abstract interpretation.
I could do it.
I'll let you do that.
Yeah. So you can imagine or just go look at a recursive knock interpreter. If you go look at lusmink and hoon.hoon, it's a knock interpreter written in Hoon. It's literally just like structural recursion matched by cases on knock, right? When we say abstract interpretation, what we mean is code that has that exact same structure, but rather than pushing nouns through the knock, we're pushing some other data structure through the knock to accumulate information about the program itself. In this particular case, I'll go into exactly what those data structures are more in a minute, but basically we have a way of masking nouns to say we know this part of the noun, but we don't know this other part of the noun, or we intentionally forgot this other part of the noun, precisely, as Joe said, so that we don't over-specialize on data, and we only actually depend on the parts of the subject that we used as code. Roughly speaking, in Hunyuket, we want to discover what the batteries of the cores are, and in particular, which formulas in the batteries that we actually used.
Is that conceptually, is that symbolic execution? Or?
That's another term for basically the same thing.
Okay.
The PL people will draw very finely sliced distinctions between these, but the high-level idea is the same thing.
Yeah, and the really basic part of this that you run into quickly is because you are not fully, materializing all values of the computation, and you're not fully materializing the result, you don't have your normal terminal conditions for loops, for recursive code. They're not there. And when you encounter a branch, you take both branches. So this explodes very, very quickly unless you have some strategy for dealing not just with local recursion, but any kind of mutual recursion. Without some guard against that, you automatically have an infinite loop. So that guard is this third category. As we descend through layers of analysis, we track the formulas that we've encountered and the subjects that we had for them. And before we analyze through a call, we check, does the formula equal something that's on this logical stack? And is the subject compatible with the best guess we have right now of what that computation does? Because we don't know what the computation is until we're done. Each new call that we analyze through could add more knowledge to anything that's on the stack. And so this is why it's pseudo-recursive. It is a guess at the time of encountering it that this is recursive, mutually recursive, so on. And anything that we guess is on a recursive code path cannot be finished. The analysis cannot be finalized until the whole transitive closure of the recursive code path is finalized. Because it is only then that we know we've saturated our knowledge of everything that is called underneath all the way through, and then we can double check that our guesses are correct, and then we can finalize it. Or if our guesses are not correct, we have to do something else.
So is it that if you didn't trace that through all the way, you would be leaving some subject knowledge on the table, like you wouldn't learn as much about
It would
No.
actually just be wrong.
You may have guessed that something was recursive that in fact was not actually recursive.
Yeah.
Now, this is theoretical. We have not been able to hit this code path. We don't hit this code path in Hoon, and we have not been able to produce an example that hits this code path. It's possible that this is approaching Quine territory, but it's clear that at the time we don't know. So this is the only way to be sure that the analysis is correct.
I was just curious, like, I'm trying to think of an example of something that would look recursive but isn't actually.
We have also been trying to come up with that example for months. Yeah.
Because we don't have our trees can't be nested?
No. It's literally because, so you have abstractly you have a call stack, right? Because remember, abstractly you have a call stack, remember, so because you're abstractly interpreting knock. And so in order to be done analyzing a point in this call stack, you have to be done analyzing all of its children. And one of the things we're analyzing is exactly which points in the subject do you actually need to fix as assumptions in order to be able to use this code path, right? So when we encounter a child of this, that somewhere further down the stack that looks like it recurs, so I think of call stacks as growing down. I'm sorry if that will be confusing, but you say it's normal because you, but it is. Anyway, I run into this confusion. You look back up on the call stack and you say, right now, it looks like this subject is compatible, but I could later discover from this child or some other child of this thing that I think I recur back to, that it actually needs a piece of its subject that I didn't know it needed at the time I guessed at recursion, where it actually differs from the subject at the child call site. And then it is really hard to actually construct an example, and as soon as I find one, I'll be very happy, because then I won't have to like walk you through the steps. I can just show it to you. But we haven't been able to discover or construct an example where this could happen. It's just clear in the analysis code path that it could happen. Like just looking at the information you have and what information you could discover later, it's clear that it could happen.
The next category. We do not know enough at this call site to resolve the formula. So we're tapping out. This is an indirect call. We're moving on. All of those categories preclude analysis, right? Those are all of the different ways that we short circuit a call site. Otherwise, we go into analysis, and if, when we finish analyzing the subject and formula at this call site, we have completed the transitive closure of any recursive paths underneath it, and it is not on any recursive paths underneath, above it, we finalize it, write it out to the code table, make it available for memoization. Otherwise, we cannot finalize it. And now I can talk about this thing that I've skipped here, mellow eyes and mellow head. So as soon as I implemented the spot hand tracing, what immediately became clear, let me see if I can find, I'll just go to the beginning here. It immediately became clear that in the Hoon compiler, because every arm effectively calls every other arm, nothing was going to be finalized until the entire compiler was analyzed. And in the meantime, you would analyze the Cartesian product of every code path through the compiler, which is why I gave up after 2 days.
So it's really important to keep in mind that you don't have, the whole point of what we're doing here is that you don't have functions and you don't have named procedure blocks. You start with a subject and a formula. And so what we're actually analyzing is call sites, not, you don't get a piece of, you don't have a list of procedures and just go analyze those procedures, which is what you're doing in a normal compiler. We don't have that. We're trying to more or less discover that list of procedures from what our code will dynamically invoke. So this is where it gets to, if you don't have memoization, every way that you could reach a call to add, let's say, will result in you, without any kind of memoization, will result in you reanalyzing all the way through add again and generating even more call sites. And this is fine if you can memorize, but as Joe said, you basically can't fully memorize in the finalized conception in Hoon.Hoon. And so it really, the set of call sites just grows absolutely enormous.
I'm curious about this, because when I think of a call site for add is something like, you call add 3 4 somewhere, you call add 5 6 somewhere else.
Right.
Those subject and formulas look exactly the same except for the sample slot.
Right.
So how is that different from normal, analysis in some other language where there's everything surrounding the argument is the same, but the argument is different?
Because in another language, I have a labeled procedure called add, and I analyze it, and I know about it. And then I go on to analyze things that call add, already having analyzed add. I have all my, I've marked down all my procedures, right?
Yeah.
And if I have something that looks like eval, I tell people, don't use this unless you have to, and then I skip it. But all we have is eval. I don't have named procedures. I don't know what things in my subject are procedures. I don't know, hey, this is this is a core and this is the battery, right? I don't get to assume any of that. So it's not just that it's completely untyped. There's no labeled procedures and there's no call form. The only invocation form is eval.
So the reason why we're just running on this big tiny is just a question of scale?
No, it's as Joe's saying, it's because in hoon.hoon, it's basically one giant mutually recursive state machine. The way that the Hoon compiler is written is one giant set of mutually recursive things.
It's just a performance problem, right? It's a severe performance problem.
But the performance problem emerges from this mutually recursive nature, not just from the number of lines of Hoon that are in the thing.
Right, so this deep tiny doesn't have this structure where...
Exactly. It has state machine structure, but not the giant, fully interconnected web of mutual recursion that Hoon.Hoon has.
I think we should probably time to punt to your presentation. And I just want to say one more thing. The technique here is very similar to what JIT compilers do. The difference here is the scale of ambition in this project, basically. So JIT compilers, JIT stands for just in time, and they're normally deployed inside of slower interpreters. They will watch for code. As code gets hot, they will then flip into another mode where they trace the execution as they interpret that code and record which branches they took, which function targets they resolved, all sorts of things like that. When they're done doing that trace, they'll construct a guard that goes at the top of that section of code and says, here's the things we have to check. Here's the things we have to look at in your environment that will say, the assumptions of this trace still hold. We can now jump into fast compiled code, and then they'll compile to native code anything underneath that trace, underneath that guard. This is how JavaScript goes fast. This is how Lua goes fast. This is how Java goes fast. This is how everything in .NET goes fast. This is a very, very effective technique. But it is deployed in small pieces. The assumptions that are made are usually vast. Oftentimes, they will not compile any branches, right? So they will guard on which side of each branch you take all the way. The trace is only valid, for a particular path through the execution. And most importantly, they only do it for hot code. This approach is very similar in the tracing and guarding aspect. But the difference is we want to do it for everything. If we were going to scale down and say we will deploy this like a JIT, when code gets really hot, we'll do a little analysis over here and we'll just try to expand our scope of knowledge a little bit. Where I started with it, it would have been just fine, right? The totally tractable level of performance for large pieces of code that weren't, let's be honest, a big tangled ball of mud, massive, a beautiful, recursive rhizome. And so what we treated the compiler as a shit test for the analysis. If we can cope with this, we can cope with anything. If there's time, I'll come back at the end of the presentation and talk in detail about the end of the story. But it's clear from the questions now that Edward needs to go top down and explain how this approach works.
Is it worth mentioning that Paul tried to do a JIT?
Oh, yeah, I mean, I should add, JITs have been attempted for knock. The Jacques project, it's a knock interpreter for Graal VM, which is a specialized version of the JVM, and the Truffle framework, which is a specialized version of the JDK for writing JITs. And the problem is, you need some structure to hang the optimizations off. Even a JIT, you just can't give it soup. And that project died because of the size of the call stacks that we generated. While I'm giving random trivia, same author wrote a knock interpreter in Common Lisp, and that would run out of memory, garbage collecting, while bootstrapping the Hoon compiler. So we are in a corner of the world where no one is, right? The degree of flexibility and absence of structure, the sheer number of con cells that we make. SPCL is the best-in-class Common Lisp compiler. This is a Lisp. Who makes more con cells than a Lisp? Well, we do.
Thanks, Joe. So I'll try to give a high-level overview of what this analysis actually looks like. But it's actually worth starting with in order to understand why we want to do this, it's actually worth starting with the idea of jets. We're all familiar with jets and what they do for you. But when you're actually in the current way that jets are labeled and allowed to be matched, this is roughly what an interpreter has to do. You have to match a formula and a subject template. This idea might, at this point, sound a little familiar. And then when you match it, you run code that's equivalent. And when we say equivalent, we mean it produces the same output for all inputs in the runtime. And so as an example, we would use GMP to do big integer addition instead of like literally evaluating the knock for add and watching and checking how big the sun has gotten recently. You know, I said we'll match the subject and formula template. We have to do this at every eval site. There's some caching you can do. There's some things you can do. Var does, as far as I can tell, the best case in terms of how you can accelerate this with caching, basically. But you more or less wind up having to do this at every eval site. Look and see if there is a jet whose formula is this formula, and then go check and see if the subjects are compatible. So at best, you're doing a HAMP lookup at every single eval site. If we refine our goal a little bit, we want direct calls. We want to know, before we start executing the knock, what formulas we're going to run at every eval site, and then we can decide this jet question in the runtime once at analysis time, and if we know there's not a jet there, we can just go for it. My slide animation's a little messed up. So again, what's hard about this? Well, knock, like I was saying, knock does not have procedure calls. There's no procedure labels in knock. We add those in literally at the type level in Hoon, right? So without those, like Joe said, there's nothing to hang any analysis on. So our working object here is literally like, as we proceed through the analysis, we increment a counter to generate labels for evaluation sites, and we decorate those evaluation sites with data. So another way of saying this is that knock2 is directly analogous to eval in JavaScript or Lisp. Here is data, whatever data is native. You know, in JavaScript, you'll hand it a string. In Lisp, you'll hand it, you know, a quoted S expression, and it will then treat that as a program in the language, right? And knock9 is very simple to write in terms of knock2. So we actually, in the analysis, one of the first things we do is basically just reduce knock9 to knock2, and then our actual analysis only has to handle knock2. And then lastly, we have one undifferentiated input. Our subject is both the data that we need to compute over and all of our library code. Any other knock that we might run, we're either going to computationally generate, don't do that, or you're going to pull it out of your subject. So how do we differentiate this? How do we say these parts of the subject are code, and we need to fix that, and we can't, and if we get a subject that has different code in that place, we can't use the same generated code that we did before because it's going to behave differently. But these other things are just data. You know, it's the sample for your gate or a state variable in your core or whatever. There's no simple heuristic for this. So what do? Well, the broad framework is that we're going, you know, this is extremely abstract, but we're going to attempt to minimize the assumptions that we're making. Literally, what do we assume about the subject for the analysis while we maximize the conclusions, what we know about what knock we're going to run at each evaluation site. So again, our assumptions are what's in our subject. So at the end of this analysis, we want to have a template for the subject that only templates exactly the things that are code that we depend on. And our conclusions are what are our actual call targets at each evaluation site, what knock are we going to run with what assumptions about its subject. So the analysis itself, we start out with a very simple structure. I don't have the code open on my laptop. Let me,
You want me to put the code up?
yeah, let's put code up. There, yeah. It'll be easier to talk through it with the code than with the bullet pointed slides for this group. But we start with a very simple structure that I call a cape. And this is just a noun whose leaves are only lubines, right? So you either have a lubine or a pair of capes. So that's this structure, right? You guys can't see my pointer, can you? This structure right here. This literally says either a lubine or a pair of capes. What that means is I can draw a tree, and each of the lubines, if the lubine is yes or 0, thank you, Uncle Yarv, we will say we need this piece of this noun, right? We can imagine laying this tree over a general noun tree and say, okay, we need this piece of this noun. There could be arbitrary structure underneath it, but we need that. If it's a no, that means we don't need it. And then the recursive structure allows us to pick arbitrary places out of the noun and say, we need this, we don't need this. If we pair a cape and some arbitrary noun, that's a sock. And that is literally, what do we know here, right? Here's the data, and this says which parts of that noun are actually known, are actually relevant to the analysis. That's it. In every version of the analysis prior to the current one, this was the data unit that was being used for abstract interpretation. When you did a knock 1, you produced a sock whose cape was just true, because you know the whole thing, right? It's right there in the code, and the data was just the constant from the 1. When you did a knock 0, you had your subject as a sock, and you took an axis out of the cape, and you took an axis out of the data, and whatever sock came back from repairing those, that was what you knew about the result of the knock 0. So you can in general imagine how you do noun operations on this data structure, and you just do those same noun operations for knock, and you just push this through.
You want your slides back?
I'm just going to use them as an outline. So as you're evaluating a formula with this data structure, you evaluate a knock 2, and it's A2, B, C, where C is the subformula whose result is the formula that you're going to run at that site if you're evaluating knock, right? So you evaluate through that subformula, and then you look at this sock, and literally the thing that we do to say, can we do a direct call here, is that cape just yes? No tree structure, not no, just yes. Joe's actually going to show you the conditional here. So in knock 2, we say, okay, if the cape of the sock for the result of this formula is yes, right? That's what ampersand is. It's just yes and hoon. If it's not, then this is an indirect call. And that's it. That's all we're going to do. If it is, then we have a bunch more analysis to do. That's the whole test there. For conditionals, we do intersection on socks.
Yes, we do know?
Yeses, we do know. Yeah.
It's a what dot?
Oh, it's a what dot?
It's a what dot, not a what col.
So if it's anything other than we know the entire thing.
Then it's indirect. Yeah. Yeah, you have to know the whole formula or you can't do anything with it. Yes?
So if you know like both of the children are yes, does that sort of collapse the
We do normalize that, yes. Yeah. Yeah, we do. Yeah.
cape doesn't have the same necessary structure as the data.
Right. There is a yes, correct. There is a normalization step for socks that we do that yes, if both sides, if you have a pair of yeses as a cape, you should normalize that to just yes. Yeah, the cape is lower resolution than the data. So for conditionals, we do an intersection. We don't have to go into the details of that, but the rough description of that is two nouns, you analyze both branches, two socks come out. Everywhere where they're both yes and they both agree, then you know there. So literally, we're analyzing the conditional and then throwing the result away. We don't mention this variable again because we actually don't care what the result of the conditional is. We're not trying to specialize branches here. But we intersect these two results. Now you'll notice that this doesn't say sock, this says non. We'll get to what that is in a second. And for quote unquote real computation, right? If you do a knock 3 and you actually try to discriminate on is this an atom or a cell? For knock 4, where you increment, and for knock 5, where you check equality, whatever we could have discovered there, we throw away. We do not use the output of that.
The wings of ignorance.
Okay, so then we'll get to minimizing assumptions. Can we go back to knock 2, Joe? The first version of this that I wrote was insane, to the degree that I came back to it after a month of working on something else, spent a month trying to page it back in, and said, what crazy malicious entity wrote this, me 2 months ago? And it was literal like multiple explicit stacks and handing continuations back between one analysis loop that ran forward through the code, one that ran back through the code. It is, So I threw it away and I wrote something that assembled a data flow graph of the entire code, because what you need to do is it's fine. I'm using this as an outline. You need to say, I used this knowledge at a call site. So on this branch, I need to record, I used this knowledge at a call site. So now it's knowledge I depend on. Wherever that knowledge came from, if that changes, I can't reuse the results of this analysis. I need to depend on that assumption. So the current way that we do that is we track the provenance of conclusions. Can we see the data structure? Okay. So this is another tree, but unlike nouns or capes, this is a tree with data at the nodes, right? So nouns only have data at their leaves, right? You have cells and then you have atoms, so the data is only at the leaves. This has labels as nodes. This tree structure is actually what's used for map and set as well. This is the abstract data type that map and set specialize. And what's at each node is a list of a label for a call site whose subject we depend on, and where in the subject this information came from. I don't know what Joe's typing
Joe's
here.
describing tree from memory.
Oh, okay.
He's showing off.
Yeah. Okay. Yeah, so this is tree, right? Joe's mentally copying it from Hoon.Hoon. So at every node,
Terrible.
yeah. So at every node of the tree, what this does for us is this records, I saw this abstract noun so remember, again, I'm thinking of like we're talking about overlays a lot at this summit. I'm overlaying this on the abstract noun for my analysis, and I'm saying this part of the abstract noun was seen at this part of the subject at this call site. So what I need to do then, when one of these, so a non is a pair of one of these and a sock. And so now this is what I actually push through the analysis, right? So I'm still pushing socks through the analysis the exact same way, but whenever I descend into a call site, I'm tagging this structure and saying, I'm tagging this structure for the subject and saying it came through this call site. What this means is, if we can go back to knock 2, I can go update a table.
We actually do it in a loop.
Yeah. So this is where we actually, literally we just say, this is the provenance for the subject. Now we're going to add on a tag that said it came from axis 1 of the subject at this call site. We just found a new call site. We're going to say that this subject was seen at axis 1 of this call site. And we just push that through. You know, when we take an axis, we push these tags down. So when I get to a call site, I'm just going to look at this provenance for the actual formula that I know and go update a table because I know where it came from and say, okay, it says that it came from this axis in this subject. So now I need this axis of that subject at that call site.
When you say it came from, you mean it came like earlier?
It flowed through there.
Earlier in the call stack, right?
Earlier in the call stack, it flowed
So
through.
the list-
Yes.
the
Yeah.
block-
So we make sure the list is
list
filtered
of
to the
columns.
scope.
It's like
Yes.
a list of frames.
Yes.
Columns.
Yes. So now we can just go back. We don't have to push stuff back through a data structure or do weird forward and reverse execution or anything. We can just go back and update a table. And this table is, can you scroll down just a little bit, Joe?
You want to see the table?
Yeah. This table is, where's want? Want.gen, which is, I named the type. It's literally just a map from a call site to a cape. And that cape is just saying, again, what parts of the subject do you need? So based on that provenance information, what axes of which subjects I needed, I can go update this table and say I need this axis of the subject at this call site. This axis of the subject at this call site. Pat Hale is just the custom aura for a call site label. All right, so that's great. We can analyze knock, except as Joe said, we have to catch recursion. Joe already mostly talked about how we do this, so I'll kind of race through it. We actually don't throw away anything that we know, except like I said, at 3, 4, 5, we do throw some things away. But we don't actually throw away anything that we know. We separately maintain a mask of what things do we need to know. So when we go up our call stack and look, we find, we're running the same formula here as here. For each of the subjects of the call sites where that's true, we take what we look in want for that call site, we take that cape and swap it in basically to the sock. It's actually kind of a cape intersection because you could technically say you need something that you don't know. That shouldn't actually happen, but could technically happen. So you swap that cape into the sock. So now the sock only records the things that you have actually up to this point needed. And you check if that sock is compatible with the sock that you know at your current call site, right? So do you know at least as much at your current call site as what that sock says you know at the previous call site? And at all the places where they both know things, are they equal? Right? If, where's the actual huge so call here? Yeah. So this is where we grab what do we currently need from that table, we apply it to what we know about the outer call site, and then we check whether the outer and inner call sites are compatible. And if that's not the case, then this is the recursive call to continue checking up the stack. If it is the case though, then we have pseudo recursion.
let me just try to read this function real quick. Then you can ask questions, because this is, in fact, the entire key. Our sample is a call site identifier, and then two of these nouns, which is a partial noun with associated provenance, and it's just a formula as a partial noun with associated provenance, and a subject with as a partial noun and associated provenance.
Is this only in the context of evaluating not to?
This is only in the context of evaluating not to. So we've resolved the formula, and it's known.
It's known. Yeah, you can't check recursion on a non-known formula. It's
Yeah.
just indirect.
So the type for fork is overly general, because it's actually just a fully known formula plus the provenance.
Do we care about the provenance of the fully known formula then?
Yes. Although not in this function. I refactored very naively. It used to be one loop.
It was, in fact, all one loop, yes.
So we have a jar, which is just a map where the values are lists, right? We just look up the formula in the jar. This is an optimized representation of the stack, right? We have a mapping from every formula to the set of subjects that correspond to the stack. If we find the formula in that associative structure, then we take the call site label for the thing on the stack that we might be a match with and look up in this global map what portion of its subject did it need. That's what the gut by
Does it need currently? Because remember, we're still analyzing under it. And this is where the pseudo-recursion comes from.
So this is exceptionally important. All over the place in this code, we are updating want.gen at any time where we might learn that something in the overall set of things that we're analyzing needs more. We integrate that into want.gen. So the set of call sites that are under consideration is growing, and the entries in this map recording our current incomplete but accumulating knowledge of what they needed from their subjects is growing here. So this is as late bound as it could possibly be. We get the subject need for the candidate recursion site above us. That is code. We apply that to the subject that we recorded for it. So we mask the subject down to our current best estimate of what it needs. We're minimizing it, but we're minimizing it late bound at the last possible minute to accommodate everything we might have learned so far while analyzing it. And only in that nests, right? sock.sand, our current subject, nests in our current best estimate of the subject constraints for something on the call stack above us.
So
Then we record it.
If it doesn't, then it's pseudo-recursive and not recursive?
No. If it doesn't,
Only
it's not
if it
recursive at
does,
all.
It's pseudo-recursive. If it doesn't, we're just going to move on and try other things.
Okay.
Yeah, if it doesn't match it, so this is just a list traversal. This is just a list traversal loop, right? Pour is a list, and we're looking at I.pour here, and then when we recur, we look at T. So it's how you write a recursion over a list, right? And then if we don't find a match in here, we're not recursive, and we signal that by returning a null from the unit. Otherwise, we return information about the recursion.
Okay, which direction was it nesting in? It's like the new one we know
The-
less
the-
information than the old one,
No. The new one has to have at least as much information as the old one,
and it doesn't conflict.
and it doesn't conflict. Yes.
So it's only if we learn something new, right? By
Yeah.
going down the call stack, right? Then it's like, okay, that was sort of, but it's clearly like the same thing, but we've learned more about it. Then it's sort of.
No. It's literally just as far as we can tell right now, this is the same code. That's it.
It's the same.
Yeah.
And then the check is but the check is like we may have learned more.
Right. Yeah. because the socks could differ. So you could, the other way you could write this would be to also app the same cape to the new sock and then test for actual equality. App is how you mask down, here's a cape, here's a sock, I'm gonna mask this sock down to just what's in this cape. So the cape just describes partiality over nouns without including the noun. Sock is a cape and a noun. So it's literally just like swap the cape in modulo. You don't want to suddenly say you know something you didn't before. So it's intersect the cape, intersect this cape with the cape that is carried with the sock and put that back as the cape for the sock.
Oh, okay. So
Yes.
the case of like so we made in the earlier stack frame, we may know some like, you know, X and Y about the subject, and in this stack frame maybe we know Y and Z, and then the intersection is just Y. Is
that wouldn't match if we
Well,
yeah, sorry.
Let me reiterate one thing about this. As we push things onto the stack, as we descend through call sites, we remember everything that we knew at the call site. So far, we don't know what of it is relevant. So we have much more information than we need. Where's Dad? Where's Dad? So the introduction form, when we began the analysis with just a subject and formula, we make a null jar. We put the formula into it. We put the call site into it. We put everything that we know about the subject. Nothing is masked off. We don't know which parts of this are code. We don't know which parts are data. We just record everything that we know. Every time we analyze through a call site, we do exactly the same thing. We are putting data.sock.fork as the key. That is the formula that is entirely known. We are putting sand in for the subject knowledge. That is whatever came out of analyzing the first formula in the NOP2.
It's
We're not
it's the
masking-
subject that you'll eval with at the call set.
So we record absolutely everything. Again, because we don't know what's relevant. So then when we go to detect recursion, if we didn't do this, if we just checked sock nesting on what we have here and what we have on the stack, it would be way too specific. We would have over-specialized to exactly whatever we knew about absolutely everything at that point.
In particular, the way that I worked this out, I had in my head already, like, how do you not over-specialize? And Ted, you might remember, and Joe, I'm sure you remember, I was talking about heuristics to like pre-mask the subject, basically, because I was only thinking about a forward analysis at this point. And then what I actually hit was a TMI problem, where if you have a loop that's building a list by Kansas, the recursion detection subject knowledge would never match, because every time you knew that you had added one more cons cell. Because you weren't masking any data, so you call this.
basically so like you know a little bit more, which is like there's an extra
Right.
element in this list.
Exactly, right. So every time, yeah, so you just have this infinitely growing list in your subject, and if you don't have any way to say, okay, but actually the parts of the subject that are relevant, not just what do I know,
Yeah.
because you can lose information through the course of the analysis, right? We don't remember the output of NOC4, but not just what do I know, but what do I need to know? If you don't have any way to do that, you can't actually effectively detect recursion.
Is that what the want.gen is about, or are you filtering for what you
Yes,
actually need?
want.gen is recording our currently what do we know about what do we need. It's a map from call site to what parts of the subject do we know that we need right now at this call site.
Okay.
And it is a flat mapping that is global for everything that is currently under analysis, because the needs propagate backwards, nonlinear. That's how they propagate. You might be all the way down over in some corner of the tree analyzing things, and you discover
So like if F calls G, which calls H, if H needs something, then G.
then that has to propagate all the way back up But doing that structurally by actually linking the data structures as you recurse, that's the first pass that Edward talked about.
That was the data
implementing.
flow graph.
That was it was,
Unworkably slow.
one of them was impossible to understand and the other one was impossibly slow. But there's a important contrast here. Since we talked about loop, I want to show the code for memoization real quick, which is the things that are candidates to be memoized, they've been completely finalized. So we no longer have this problem of our best current estimate of what they need out of the subject. We know everything about them and everything that they need. This code looks very similar, but the check is much simpler. There's no cape masking. We're not looking at want.gen. We're not accumulating anything at the last minute. We just have formula and a subject, and we just have to do a nest check on the sock for our subject against the memoized sock.
It's we've learned more, but we haven't forgotten anything.
No, we're literally done. We've gotten past the point where you could add any needs to these call sites.
Everything that's in memo.gen, it's been fully analyzed. We know everything that it needs. The sock that we store with it is completely normalized to only contain the parts of the subject that it's going to use as code. This is the Platonic crystalline final form result of the analysis. And so while we're analyzing, when we check against that, the check is very simple. We just have to see if whatever we have matches whatever we stored, and it's done. So there's none of this late bound masking and intersecting and all of this other kind of stuff.
So what does it mean to match? Is it just equality on the capes? Or
It's still a sock.
Nesting everything. So we're going to say,
direction?
we're going to say, does the knowledge of our subject that we have nest under the knowledge of the subject that we analyze for this other piece of code? And so for every
The other code knows at least as much about the subject as we do.
No. We know at least as much as it did.
All right.
Yeah.
everything that they know, we know and match. We may know more, but it doesn't matter. We're not constrained by that. Anything that matches, we know we're the same as them.
That was all I had. Do you want to talk about melloization?
Yeah. So now that brings us back to the analysis that I was doing and the challenge, which, if I had thought about this, I would have had the old broken version ready to run, and I would have just let that run for the whole talk. And then anyway, I don't have the foresight of Puri.
Okay, we're saying basically at time. but
We're at time, yeah.
why don't you-
So
5-minute warning, okay.
the thing that we had to do, as I said at the beginning, was reuse work in the style of the memoization that we just showed you, but it's actually not done. We finished analyzing it. We can't finalize it and make it globally available. It's part of some larger recursive structure. We haven't totally saturated our knowledge of the recursive structure, so we're blocked. And the first thing
There's
that
a
we
fixed
tried,
point we haven't been able to run yet.
the first thing that we tried was exactly the same approach.
You say it's not, but it's not finished. Right? It's just, we're in a part of the code that is broken.
There are recursive, we have bottomed out the tree to everything is either analyzed to no more calls or to recursive calls, but those recursive calls go outside of us, basically. So we depend on, we need to finish analyzing the entire recursive closure, not just our call tree before we're done.
When we tried to memoize in this style, we ran in to problems in where we made judgments that things matched that were wrong. We could see by tracing the call stacks, by looking at the heads, we could see that there was 2 different runs through the code, and they were higher ordered, they passed gates along with them, the gates were different, but we were saying that they were the same. And so then at the very end, we were having to check for this particular condition, and that was really slow and gross, try to punch it out. The insight was very simple. It was precisely this thing that we have been highlighting, to memoize within a loop, which I creatively called mellowize. We do exactly the same thing as we do for memoization. We just check it in the way that we check for recursion. So each time we try to look up, are we the same as some piece of analysis that is complete but not final? All we have to do is the same song and dance of take our best estimate of what it needed out of the subject, mask that off of the subject that we recorded, check against that, and immediately all the spurious matches disappeared and the runtime of the analysis dropped dramatically. This was the entirety of the key. So this song and dance that we keep trying to explain, that we don't have visualizations for, if anybody has ideas how to visualize these overlaid multi-dimensional trees, we really, really want to create those things. Sam does. This is the entirety of the key. It is this style, this pattern of accumulating the mask of what we need on the side where we can retrieve it, we can retrieve our latest estimate of it when we need to. And we don't have to thread that specifically through in graph shape, the paths that it covered. It's just available. That's the whole ballgame.
That's it.
There's only one other thing to say, and that is, after this was done, I had the analysis running, but I had a large number of call sites in Hoon.Hoon that were inexplicably indirect.
Basically, the analysis couldn't get through them. It didn't know the formula, and it just very obviously should. Unibuy.
Here,
Yeah. Yeah.
I can say that
Unibuy. There's no higher orderedness. It's not a strange function. Like, why is it indirect? We couldn't. Joe was frustrated by this for a week, I think. This is Unibuy. Is this Unibuy or Uni-in? I mean, they're basically the same, but.
This is Unibuy. They both have the same problems. So what I would see as I trace through more and more locally is that this recursive call site was known. It worked fine, analyzed it, matched it. It's a loop, right? We're looping back up. This one was not known. And I puzzled over this, and I printed, bigger and bigger trees, and I just poked around at it.
Is it just like buck of? Is that why?
No. It's amazing, actually. It's TMI.
It's TMI on socks.
So when we go to analyze this, because we know whatever we start with,
Too much information.
I'll explain, yeah. We know that the overall map that we're dealing with, we know that it's sig, we know that it's 0, because we just happen to, hit this through the default code path of bunting it or whatever. And we know that B is 0 for the same reason. So when we make this edit, we're editing L.A to the result of the recursion. And that was poisoning our knowledge because it was saying you're making an impossible edit. You're editing through an atom.
And it's important to point out that the reason for this is that we take both sides of a branch. So we're actually branching here on whether A is sig or not, right? And whether B is sig or not. But we take both sides of that branch with the same subject in the analysis, right? So it's not actually, you can't be as restrictive as knock is here.
Right, and that editing operation on socks implemented knock opcode 10 semantics, and knock would crash if you tried to edit through an atom. So it did the same thing. It said, this is impossible. You don't know anything because you just tried to do something that's impossible. And the fix was,
Did that just crash then? And then
no,
No, you just say
it was in a unit, right? So it would just return null, and you just didn't know anything from that point on. So it was very simple. I changed the editing operation on socks to have, you know, a superset of Noct10 semantics. And if you try to edit through an atom, it says, okay, on the other branches, I don't know anything, but now we know this is a cell, and we're gonna say this is a loose, sort of dynamically typed operation where you tell me to edit it, and I'm gonna do that. And the semantics will be, if you got to this line of the program, this is what your subject would be. It's not my problem if you crash.
It's like, it looks like you won't be able to get there, but
But if you did, here's what you would have. And immediately, all the inexplicably indirect calls, there was a whole bunch of them in the Hoon parser, they were all over the place, immediately they were gone. So those two changes, what I showed you took 95 seconds. If I remove the hints from Hoon.Hoon, where they normally aren't, and turn off the printing, it takes a minute. This is not lightning fast. We complain about the Hoon compiler. It takes 20 to 30 seconds to compile itself. But this is completely tractable, and we know everything but 3 call sites in Hoon.Hoon. All of them are obviously indirect by construction. If you want to know why, I'll explain to you some other time because we're out of time here. That is all.